by James Watson and Watkins, and they will talk about exponentially improve the product formula. Yeah, James, the floor is yours.
Thanks for the introduction. Yeah, I'm going to be talking about exponential formulae using extrapolation. It's another product formula talk. You're welcome. This is with my wonderful and handsome colleagues, Jacob, Gumaro, and Nathan. And it's a combination of 3 papers, but the meat of the papers, or the meat of the talk is going to be in this paper here, linked to by the QR code. So I'll start explaining why you should care about product formulae, although the previous speakers have kind of done that already. Talk about improving product formulae, our results, the proof idea, and some extensions and future work. So hopefully I don't have to convince you guys that Hamiltonian simulation is important. It's a kind of key application in quantum computing. We want to solve problems in material sciences and quantum chemistry, but also simulation forms a kind of fundamental subroutine for other quantum algorithms, such as graph transversal or HHL if you're doing linear systems. And also, this isn't kind of like a theoretical BQP hardness kind of quantum advantage. We hope this is kind of like a real, concrete, commercially valuable quantum advantage that's going to keep us all employed over the next few years. So how does a kind of typical quantum simulation workflow look like? Well, we start with some sort of state preparation step with our initial state. We're going to implement some sort of time evolution with some approximate unitary, which approximates the full time evolution. And then at the end, we're going to do some sort of measurement or observable. In this case, we're just measuring an expectation value of an observable A. And as computer scientists, or physicists pretending to be computer scientists, we're typically interested in this middle step, where we're trying to do, or most efficiently approximate, the idealized time evolution. And typically this is done in terms of the spectral norm, so we're interested in constructing a U of t, which approximates the true evolution to some epsilon as efficiently as possible. And the first algorithm to kind of do this was the kind of first-order Trotter algorithm by Lloyd in the 90s. So in this case, just a review if you weren't here for the previous 2 talks. If we have a Hamiltonian, a local Hamiltonian, which is the sum of some local terms, h sub j, we're going to define the first-order product formula to just be the exponential, or the product of the exponential of all the terms in the Hamiltonian multiplied by some time slice. And if you go away and you expand the Taylor series, do a truncation, you can see that if you take a single time slice or a single time step, you get an error bound that scales quadratically in the parameter t. And if I now apply this product formula multiple times, if I apply it r times, which I'm going to call the number of Trotter steps, with an appropriately chosen time slice, we get a quadratic error bound scaling as t squared over r. And so naturally, if I choose, or if I want to achieve some error epsilon, I can choose my number of Trotter steps to go as t squared over epsilon. And here, the number of Trotter steps is more or less a kind of proxy for the overall kind of gate count, if you want, at the moment. Okay, so fantastic. And of course, people have gone away and they've developed higher order product formulae. There are many of these, like the higher order Trotter-Suzuki formulae. And they kind of broadly take the same form, which I've just written here, kind of generically, P of t as a product of exponentials of the Hamiltonian, but now we kind of appropriately weight the exponents so that some of the terms cancel out. And generically, I'm going to say that we have a pth order product formula, if, when we apply it r times, we get an error bound that scales as t to the power of p plus 1 over r to the power of p, where p is some constant that we've chosen based on our algorithm. And so, of course, if I want to choose, or I want to achieve some error epsilon, I need a number of Trotter steps, which scales as t to the power of 1 plus 1 over p, divided by epsilon 1 over p. Fantastic. OK, but if you are somebody who's involved in the literature at all, you're going to come to me and go, James, you rube, we have all these other fantastic algorithms for quantum simulation, quantum signal processing, these post-Trotter methods like LCU. These are asymptotically optimal, as other speakers have pointed out. Why do we care? Well, I subscribe to what I've endearingly called the gospel according to Andrew Childs, that we heard about earlier. Sorry, Andrew, wherever you are. So despite the worst asymptotics of product formulae, they often actually perform really, really well. And this is a graph from a previous paper where we're looking at Hamiltonian simulation to some precision. And you can see that the gate counts for fourth order product formulae actually outperform quantum signal processing quite significantly. And this may not be generically true, but at least in some cases, it is true. And other people have also noted this. I shouldn't pick on Andrew so much. OK, so why is this? Well, as we heard in the other talks, including Andrew's talk, post-storage methods suffer is maybe laying it on a bit thick, but they have gate overheads and qubit overheads associated with their implementation, and they often don't achieve commutator scaling in the terms of the Hamiltonian. On the other hand, product formulae have a lot of kind of like very nice properties which are kind of implicit in their construction. As we heard earlier, they achieve commutator scaling in the norms of the Hamiltonians. They don't have any kind of inherent qubit or gate overhead in some sense. And they often kind of conveniently exploit the system's kind of inherent physics, the entanglement structure, as we heard earlier, but also the Lieb-Robinson bounds on locality. And as I've just mentioned, they often perform very well in practice. This is despite the fact that they have less than optimal circuit depths. But even if you don't believe me, you don't believe smarter people than me, at the moment, product formulae are kind of the only thing we can really implement. So on my flight here, I had a nice 10 hours on my plane. I tried to look through the literature and see what kind of algorithms people are implementing. And this very scientific graph came out. And as you can see, there isn't really much in the literature where people have kind of really convincingly implemented LC or quantum signal processing, maybe. You can maybe debate that graph with me later, but it's very hand-wavy. OK, so at this point, I hopefully convinced you that we should probably try and improve product formulae as much as possible. So how can we do that? Well, sorry. For the rest of this talk, we're going to be interested in a slightly restricted task for the purposes of improving product formulae. So we're going to be restricting ourselves to the task of observable estimation. So I'm going to now be interested in, given some observable that I'm interested in learning expectation values about, can we construct an estimator, A tilde, which approximates the true expectation value, time-evolved expectation value. And the way we're going to try and make some progress on this is by looking at our quantum simulation workflow that we mentioned earlier, and we're going to try and combine these kind of two final steps, the time evolution part, the algorithmic part, and the measurement part. And the kind of object that we actually have access to in the lab, or I guess on the quantum computer, is of course going to be the kind of time-evolved, or the trotterized time-evolved expectation value. So here, this is just the expectation value of my local observable, or any observable, in fact, after I've evolved it for R steps, R trotter steps, and then measured it at the end of my computation. And we're going to find it a little bit more convenient to not consider the number of trotter steps, but instead work with a different parameter, S, which is the inverse number of trotter steps. And so the kind of object of interest is going to be the trotter formula to the power of 1 over S. OK, fantastic. And what we can do, or what we're going to do, is we're going to define a function of the expectation value as a function of S. So here, S, this is literally just the expectation value as a function of the inverse number of trotter steps. And this has some nice properties. And importantly, it's defined for real value S's, including negative S. But importantly, as we take the limit of S equals 0, or goes to 0, we have the limit of an infinite number of trotter steps. And so we achieve the exact, or the idealized Hamiltonian evolution. And this is the kind of quantity that we're going to be using and trying to estimate. So now I'm going to hand over to my collaborator, Jacob, who's going to tell us how we can estimate this quantity.
OK, thank you so much, James. So hopefully we've motivated now sort of the task at hand and illustrated the basic idea. And now I'd just like to go into more details into the exact protocol we're going to run, talk about the theoretical results that we derive, and some extensions towards the end. So let's get into some of the details. As we've just outlined, we can establish this functional relationship between the quantity we're interested in observing, which we call f of s, and the trotter step size s. Say, for example, it looks something like this. I've highlighted with the dashed line f of 0, which is our exact quantity of interest. The first thing we're going to do in our approach is to choose some symmetric interval containing the ideal value s equals 0. The size of this interval necessarily depends on the parameters of simulation. So in particular, if we need to simulate for longer or have high precision requirements, we'll need to take this interval smaller, which will correspond to higher computational costs. The quantum part is simply taking product formula evolutions for different Trotter step sizes. For those who are curious how you do this for negative s, it's really nothing special. It's just take the inverse formula. It's not too complicated. And what we'll do then with this data, now everything is purely classical. We're simply going to perform a textbook polynomial interpolation whose degree matches essentially the number of data points. And our estimator is simply going to be this polynomial evaluated at 0. In other words, the constant term for this polynomial. So that's the algorithm. It's relatively straightforward. There's a few details I'll discuss later. But I'd like to move on into some of the theoretical analysis we do and some of our results. So we investigate two natural metrics of cost. First of all, the total circuit complexity. To be a bit more precise, we're going to look at the number of queries we make to the exponentials of the terms in the Hamiltonian. In typical scenarios, these terms are sort of unit cost, and so this is sort of a natural metric. We will also look at maximum circuit depth. This is particularly relevant for today's noisy devices, which are limited in computation depth due to decoherence and other factors. In addition, we look at two broad categories of measurement schemes, one which is more quantum, one which is more classical. So we consider a coherent measurement template in which we encode our expectation value in some amplitude and use some amplitude estimation scheme, perhaps, to extract the quantity of interest. This has the benefit of achieving Heisenberg limited performance in the precision, so it's sort of optimal in the generic case, but requires relatively longer circuit depths, uninterrupted computation. In contrast, you could simply do repeated measurements in order to get your expectation value, coming with quadratically worse error dependence. However, we can do shorter circuits just by repeating the same basic circuit over and over again. So we're going to arrange those different categories in this small table you see here, and I would like to present our main theorem in the form of the query complexity for each of these categories. So I'll start with the leading order of the precision scaling. The dominant factor in this case is coming from the measurement protocols themselves. So if you look at the top row, which is the coherent measurement scheme, we get the anticipated 1/epsilon scaling, which is just coming from the whatever measurement protocol we're using on top of our extrapolation. In the bottom row, we have the 1/epsilon squared, which you expect just from statistics. And on the right, we don't get anything for this piece because our measurement protocol does not, we just have sort of a circuit of fixed size here in terms of the measurements. Now we do pick up from our extrapolation some polylogarithmic factors. The degree of this polynomial is not so severe. It's order 3. So we're not adding too much overhead. I'd like to highlight that in the bottom right, we see that we have a only polylogarithmic error dependence in the total procedure. And this is formally exponentially improved over product formulas alone, which depend polynomially on the inverse precision. And finally, I'll show you the scaling with respect to the total simulation time. If you're familiar with product formulas, you'll see nothing surprising. We don't have any trade-off with the total simulation time. We get the typical expected scaling. And this lambda factor indeed depends on commutators of the Hamiltonians. So we get commutator scaling. So the idea here is we've sort of mitigated effects of the errors that are solely due to Trotter alone for this task of time-evolved expectation values. So with my remaining time, let me explain some of the theory that goes behind obtaining these results. So recall that we can write for the observable A sort of Heisenberg picture evolution in terms of the product formula for a given step size S. What we're able to do in our work is show an explicit error series about the ideal value of S equals 0. These E sub j are super operators. They're linear operators on the space of observables. And in particular, their size is commutator dependent, and so this sort of leads into the commutator scaling that we find. We're able to derive this sort of bound using a combination of two tools. One of them is a certain form of the BCH expansion, which is naturally represented in terms of right-nested commutators. So we do find that quite useful. The other thing we do is multiple applications of Duhamel's formula to bring those terms out of the exponent in a way that is more manageable. So what is this? Why is this helpful? Well, take, for example, our interpolation protocol. There's sort of this textbook error bound you can write down that looks very much like a Taylor remainder error. And it depends on the size of the derivatives of our function of interest. So with this explicit error series, and we don't even need to represent it as an error series, we can also have a remainder term, it sort of becomes very easy at this point to just write down an error bound, turn it into a query complexity. Another crucial ingredient is robustness. We can't calculate the values of f perfectly. And moreover, we don't want to be too picky about our choice of interpolation node. So I'll start with the values. So in terms of the data values, it's sort of this pretty standard numerical results for polynomial interpolation that the Chebyshev nodes are sort of ideal, in the sense that if I have some error in my data points, it doesn't drastically change the interpolating polynomial. This is not always the case for any choice of nodes. And this is where some of the polylogarithmic factors come in our main result for our approach. So they're just logarithmically sized. Another crucial point is that we don't want to choose the exact Chebyshev nodes because, as many of you may have been thinking, we don't want to choose actual real values of S for our algorithm. We use it formally, but we would like to take integer Trotter steps, right? And so what we're able to do is take approximate Chebyshev nodes, which are reciprocal integers corresponding to normal Trotter product formula evolutions. And using this mathematical result from 2018 by Vianello and Piazzon, we are able to show that sort of this has minimal impact on the well conditioning. So this is a pretty important improvement over our first work on this topic, which is part of these papers, where we have to consider some fractional query scheme in order to use the Chebyshev nodes. This is totally unnecessary, and you can just do product formulas. So for this talk, we focused mostly on polynomial interpolation and time-evolved expectation values. Let me talk about a few other aspects that I don't have time to go into detail. We do an entirely analogous sort of analysis for Richardson extrapolation and find very similar results. Our first paper explores similar approaches for estimating eigenvalues of your Hamiltonian. My colleague James has extended these results to randomized product formulas. One crucial aspect to get these results was to not have to use fractional queries because those are much more difficult in the randomized setting. And finally, our approach is consistent with classical shadows. So if you use classical shadows to estimate many observables for different Trotter step sizes, you can simply perform this, provided that each of those expectation values is sufficiently accurate. You can use our extrapolation techniques to mitigate the Trotter error from those observable calculations. So with my remaining time, I'll just summarize that Trotter often outperforms theoretical expectations, and though those theory is gradually improving, as we've seen, we see that improving Trotter itself is a valuable enterprise. We've shown how to use classical extrapolation techniques to effectively mitigate Trotter error. And our method is simple and versatile. It's just Trotter evolution. It works for any p-th order formula, randomized formulas. It's compatible with multiple different measurement schemes. And so hopefully this can be a useful primitive for applications. So for sake of time, I think I'll just show this remaining slide. Thank you for listening, and we're looking forward to questions.
nice talk. It seems like for the interpolation to work, as you take S to 0, you need like some kind of smoothness condition, or you'd expect you're only able to get so close, right? So how are you able to, or on what basis do you get that kind of like smoothness that you know that your analysis will be valid in the S goes to 0 limit?
Sure, I can. Sorry. That was a very good point, and we didn't touch on it very much in the talk. I did show very briefly we had this sort of error series expansion for the time-evolved observable. Implicit in that is that there is some analyticity. So in fact, in a neighborhood of the origin, s equals 0, this function is analytic. Our guarantees of analyticity depend very much on the difficulty of the simulation. So this is why I mentioned that this interval gets smaller and smaller. The intuition there is like you can't use Trotter to, if your Trotter approximation is bad, for you're taking too large of step sizes, you can't magically do longer evolutions just by doing some classical stuff. So you need to have good estimates on each of your data points. But the short answer is yes, there is analyticity, in fact, about the origin.
If I could add for a moment, yeah. The radius of analyticity is basically where you get a Formulae Hamiltonian. So you can do this extrapolation, provided you have a Formulae Hamiltonian that is not like diverging. And that's basically what determines the size of the steps that you use. Thanks for the question.
Question over there.
Yeah, maybe this is connected to the first question, but is there any assumption on the operator A that gives you this polylog 1/epsilon factor?
As in the observable?
Yes.
No, it doesn't have to be local or anything. It's just has bounded norm.
But if it's true for every A, doesn't it imply maybe you can do Trotter simulation of the state? It's polylog 1/epsilon as well.
So I think so for our costs, we only count queries to the product formulas. Certainly, in these protocols, you need to somehow introduce your observable. So if your observable is very difficult to implement, then that will indeed contribute to your costs. That being said, it has sort of maybe no effect on these results. One very practical case you could have is you have some block encoding of your observable that introduces some amount of overhead depending on the observable. So these are things we were showing sort of the Trotter exponentials, but it's implicitly there. So depending on your observable, you'll have to factor that in.
Thank you.
Yeah.
Thanks.
I actually have a question. So your step size is less than lambda times t. I mean, that's a very big.
I don't think it should be less than.
Require step size to be less than O. I mean, that's an extremely large step size. I assume you're still doing small steps.
Yeah, we're still doing small steps.
So what does that requirement
I think that might be
mean?
a typo.
Oh, sorry. Yeah, that is indeed a typo.
So it should be. What should it be?
Yeah, so that capital T, so there's sort of, so when I was showing the illustration of the algorithm, I had this interval from -a to a. So really what we just need is, like, we basically need to bound lambda of any s times capital T. So S, or you could say like T over R, right? So your Trotter step size in time. You just need that to be bounded by a constant. It's something like 1 in this case. And then this procedure follows through. Yeah, so that's a typo. Good catch.
Thank you for the nice talk. So is there any numerical test of this method on actual Hamiltonian to see how this method works on Hamiltonian?
Do we have numerics in here? I thought so.
We do. You want to talk about them? I have our one extra slide.
Oh, one extra slide. Oh, I didn't realize you didn't do that. Yeah, I mean, so this is just fixing the simulation time and increasing the number of nodes that you use in your interpolation. And so at the bottom here is the number of Trotter steps that you actually implement. The y-axis is the error, and you can see that you get an exponential decrease in error when you use either extrapolation method, polynomial interpolation, or Richardson extrapolation. And the black dots are just standard Trotter. So you can see there's a big exponential distance. Isn't that fantastic?
Yeah, and I also, if you're getting worried that this is looking like magic, I want to comment that this is assuming like ideal values of your measurement, right? So if the more typical behavior is, however precisely you measured your trotter of all the observables, you're going to flatline to that. And what that means is you've removed the trotter error to a very large degree, and you're left with whatever sources of error went into your data.
Thank you.